Okay, good morning everybody. We are going to continue from the class of yesterday. Just to remind you, you're going to be tired of looking at this picture and the Schottky barrier at the surface. We have seen that the surface of a semiconductor behaves really very complex way, but essentially we have acceptor levels at the surface. The electron from the conduction band drops to those states the band bending produces, so the surface in energy goes up, and the equilibrium is established when the amount of charge of those acceptor states is equal to the total amount of charge, that was in what now is the depletion region, right? The energy, of an state here, an absorbed particle that produce this acceptor level, to start is the energy needed for a neutral to absorb, but we have to sum up the energy due to the electron which now is here. So the total energy of absorption is not only the energy for neutral, but you have to sum up the energy for an electron. This, in fact, this whole thing is a scheme for the energy of electrons, right? So the extra energy is given by this difference, this minus this, so that the extra energy of an absorption when it is ionic state, when it's charged. So we saw what Falkenstein was saying. Yes, this is the absorption rate. So this is directly relating to the number of particles that impinges on the surface, and the desorption rate has to be the same as the absorption rate in equilibrium and steady state. This is going to depend on, it's going to have two possibilities. We have the neutrals that can desort, and those who are charged, the ions that can desort. The key of all this is that Falkenstein realized that this rate of desorption is very low. It's very low because you have an exponential, an extra term. So what he proposed is that most of the desorption takes place through neutrals. That's something that, yes, tell me.
So coming to sticking coefficient, is it temperature, material or gas dependent?
If it depends on the material, you say?
I'm asking, sticking coefficient depends on what? Which parameter?
What depends on this?
What does S depend on?
Oh, S, the sticking coefficient?
Yes, sir.
Oh, yeah, that depends specifically on the type of surface and the type of gas atom who is absorbing. In our case, practically is one. All the particles that are arriving at the surface, they absorb at the surface. Fortunately, a problem less. We have enough problems now. So, how many of the particles that are absorbed at the surface are charged and who are not? Well, that is determined by the Fermi-Dirac function. So it has this form, and eventually with these equations we put them all together and arrive to what is called an isotherm. It's relating the pressure of the gas and the coverage. At 300 K, which is 300 C, which is a typical temperature used in tin oxide, the coverages are very low. They are just a few percentage. So this term we can get rid of that term, and essentially the coverage is proportional to the pressure, right? So, and if we relate all the variables we had before, this beta factor has this shape, this form, and we have here a term which is very small. So essentially that is telling us the desorption is taking place through neutrals. Okay. I extended these ideas of Falkenstein to adsorption when the molecule, that is, we have a molecule adsorbing and that molecule dissociates in two atoms. So things do not change much. We have a square root here, and this is the form of beta. Yeah, and essentially equilibrium is reached when the amount of charge in the bulk, I mean in the depletion region, is equal to the amount of charge which is at the surface. Yeah, we need neutrality. Okay, so after looking at all this, which is quite complicated because we have the barrier, we wanted to check how things were going on, avoiding all the problems that the barrier is generated, yeah, at the surface. So a way to avoid this and simplify our problem and solve experiments was to use very, very small grains. If you have very, very small grains, we have no room for band bending, and the bands are practically flat. So if we accept that, yeah, now we have no room for this to develop. Yeah, so everything is almost flat. Yeah, the bands are practically flat. We have no much things absorbed at the surface. This is going to be very conductive because the Fermi level is going to be up. If we don't have any acceptor level at the surface, so the Fermi level is going to be quite close to the bottom of the conduction band. We are going to have many electrons, yeah, and this is going to conduct electricity quite well. As soon as we have acceptor states, yeah, which are at the gap, most of the electrons are going to drop there. Yeah, only a few of the conduction electrons are going to remain at the conduction band. The Fermi level is going to go down, and this is going to be the situation when we have many oxygen atoms adsorbed at the surface. Yeah, and we can do rare band bending. This is going to simplify our calculations, and we can consider that regularly in an atmosphere where there are a lot of oxygen atoms, most of the conduction electrons that were originally at the grain are going to be in this acceptor levels at the surface. So this is going to be the initial situation. If we reduce the amount of these acceptor levels, the Fermi level is going to be a little go up. We are going to have more conduction electrons, and the conductivity is going to be larger. That is going to happen if we introduce some other species like hydrogen or carbon monoxide, which is going to take oxygen from the surface, so it's going to reduce the amount of oxygen at the surface, and then the film is going to conduct electricity better. And that's the way the sensor senses. Yeah? This type of sensors work. Okay, we were here. So we are going to do in a slightly different way what I did in my talk. For those who were there, sorry, I'm going to repeat some things. And we want to know what is the response to gases. Yeah, what type of response? How the sensor responses. So to do that, people regularly use what is called the law of mass action. I'm going to present two models. Yeah, model 1 and model 2. Model 1 is the Japanese model. In Japan, they use this model. Model 2 is the German model. This is what the Germans have been doing. I'm talking about the most known groups working in gas sensors based on oxides. Well, I'm going to do it first because people do not agree, and now there's been more consensus that the oxygen adsorbed, not like this, but like this, yeah, doubly charged on the surface. But we are going to do it in both ways because people are not completely convinced what type of ions we have on the surface, what type of oxygen ions we have on the surface. So people agree or say that oxygen adsorbs on the surface, ionizes, yeah, and eventually have two oxygens with one charge if it is singly ionized. We apply, I'm going to do it with this column. If you apply the mass action law to this chemical reaction, assuming it's the only thing we have in the atmosphere, in the ambient. So remember how this is done. This is a oxygen in air, so this is the pressure of oxygen multiplied by, we have 2 electrons, so we have to put here the density of electrons to the square, because this is a stoichiometric factor. Do you remember how to do this, right? You have it done in chemist classes. So the product of this, which are the reactives, it has to be equal, proportional. We have constants here, but I'm putting proportional. All we want is to know the ratio between the variables. This is the density of oxygen at the surface to the square, right? Do you agree? This is coming from this, applying the law of mass action. Now, we have seen that most of the electrons, since the Fermi level is quite deep here, most of the electrons are here. So this is a small percentage of the original electrons we have. If this is the situation, the amount of charge I have here is practically constant. It's practically all the electrons that were here before, most of them. So the amount of charge here I have here is practically constant. What I'm saying is that the density of surface charge is practically constant. So if this is the case, we can deduce that the density of electrons at the conduction band is proportional to 1 over the pressure of oxygen to 1/2. Do you agree? Yeah. N is proportional to 1 over the pressure of oxygen to 1/2. That will be the dependence of the electron density at the conduction band as a function of the oxygen pressure, right? So that's going to be the how the conductivity changes with the oxygen pressure, because the conductivity is directly related to the density of electrons at the conduction band. Well, if this is not the case, but we have oxygen doubly ionized, now this equation has to be written in this way. Oxygen arises, a molecule of oxygen arrives to the surface, and now it's going to need 4 electrons, to have 2 oxygens doubly ionized. If we apply now the mass action law to this chemical reaction, we have n to the 4th. It's the same than before, but with n to the 4th. As before, the density of charge at the surface is practically constant, so the density of electrons in the conduction band is going to be proportional to 1 over the pressure of oxygen to the 1/4. So depending on the type of ions that are absorbed at the surface, we're going to have 2 dependencies for the conductivity different as a function of the oxygen pressure, right? Well, the Germans do a similar treatment, but they write down the question this way, and this is done by chemists in many situations. They just say 1/2 of an oxygen molecule plus 1 electron give us 1 ionic, 1 ion of oxygen. And this seems to be quite similar to this. If we think we are dealing with moles, these represent not particles or molecules, but moles is the same. Here we're saying a mole of molecules of oxygen, they need 2 moles of electrons to produce 2 moles of oxygen absorbed at the surface and ionized. And here we are saying that 1/2 mole needs 1 mole of electrons to produce 1 mole of oxygen at the surface. It's the same. It's just the second one is everything just as the model 1, but 1/2. That's it. 1/2 of what we have in the left side. So in principle, it seems to be is the same. So far it's the same. we apply the law of mass action, and here we have N, the density of electrons, the pressure of oxygen to 1/2, because the stoichiometric coefficient is 1/2, proportional to the density of ionized oxygen at the surface, so sigma S. Well, if we now want to know the dependence, this is constant, so the dependence of electron density as a function of oxygen pressure, yeah, what's going to be? 1 over the pressure of oxygen to 1/2. It's exactly the same as the one on the left, because the one on the left is just the square, yeah, you get this equation by taking the square of both sides of this equation on the right, so it's the same, right? And if the oxygen adsorbed at the surface is doubly charged, well, instead of this equation, we're going to have this equation. We're going to need 2 electrons here. We apply here again the law of mass action, and what we get? N to the square, pressure of oxygen to 1/2, proportional to the density of doubly ionized oxygens. And the dependence of the electron density as a function of the pressure of oxygen is 1 over pressure of oxygen to the 1/4. It's the same than the other model. So far you could say, well, they wrote things in a different way, but essentially it's the same. Yeah, well, we are going to see that it's not exactly the same. The problem comes when we introduce a reducing gas, typically carbon monoxide or hydrogen. People accept, or everybody agrees, that carbon monoxide of hydrogen, yeah, takes oxygen absorbed on the surface, yeah, they form a molecule that dissolves and releases, in this case, 1 electron. Here we are dealing first with ions having only 1 charge, yeah. So now we are not in equilibrium anymore. This is a situation of a steady state. So under a steady state, the amount of oxygen should be constant. And for that to happen, the absorption and the desorption rates have to be the same. So we can equate, yeah, the desorption rate and with the absorption rate. Well, oxygen is absorbed at the surface at this rate. It's going to be proportional to the pressure of oxygen and a square. Yes, as we did before, yeah? Here. This is the absorption rate. And how is the oxygen going to be desorbed? Well, as it was doing it before. Yeah, since it's a second order reaction, it's going to be proportional to the density of ion oxygen to the square. And but now we have another channel, the channel due to the reducing gas. And this channel is going to be proportional to the amount of the pressure of the reducing gas and the density of oxygen absorbed at the surface. Well, this would be the situation, but we are supposed that when we are introducing a reducing gas, the reducing gas is going to play the main role. If not, nothing is going to happen. So this term has to be dominant if we think that the reducing gas is doing something. So in principle, we can say that this is practically 0. Yeah, it's not relevant. And then this term becomes equal to this term, and we can find how much is the value of the electron density. Yeah, essentially it's proportional to this, the pressure of the reducing gas divided the pressure of the oxygen gas, assuming, as we said before, that the amount of charged oxygen, amount of charge at the surface is practically constant. So model 1, we arrive to this, yeah, to this ratio. That is the amount of the density of the electrons in the grain is going to be proportional to the pressure of the reducing gas to 1/2 and inversely related to the pressure of oxygen to the 1/2. right? Well, instead of that, if you use model 2, now we have that the rate of absorption is given by this form. Yeah, we go back, remember, model 2, this is what we have on the left. Yeah, the reaction rate is this one. So we do the same here. This is the rate of adsorption, and the absorption is going to be proportional to the density of oxygen absorbed at the surface. And now we have the new channel, which is related to the reducing gas. So assuming again that this term is small compared to the second term, assuming that the reducing gas is playing the main role, we arrive to this conclusion. Now the density of electrons at the surface is going to be proportional to the pressure of the reducing gas and divided by the pressure of oxygen to 1/2. So we arrive to a different conclusion. Now things are different. You see, before it was proportional to the pressure of the reducing gas to 1/2, and now it's directly related. Yeah, and what is whose model is right? Whose model is wrong? Any comment? Is this correct? What is the rate of adsorption? Yeah, should be proportional to what? You know the kinetic model of, gas kinetic model. Yeah, in the gas kinetic model, you know that the pressure is related to the number of times per unit time that molecules are, knocking on the surface. So this is telling us that the number of molecules of the gas for arriving at the surface is proportional to the square root of the pressure. Something's wrong. This should be linear with the pressure. So this is obviously wrong. Okay. Well,
you can also find this experimentally, right? You look at the current as a function of the pressure of the diffusion gas.
Yeah, it could be done. That would be it's not going to be easy because you have you're in equilibrium in a steady state, so then you're not going to have you're going to have a steady state current, maybe in a transient. A good idea. We can try to make that experiment to measure the current, which is as a function of time that is arriving at the surface when you make a quick change in the pressure of the Okay, we can write down that paper once we have the results. Okay. So these two models are in many papers, but in many papers published in the literature. And so what I want to show you is that there is consensus on the basic mechanism, the general ideas. People agree on that. But these details, when you want to go into the details, people do not agree. But they are not irrelevant details. They lead us to different responses, to different results. Yeah? Okay. So I have to add one more model. Now I'm going to show you that both models are wrong. Not only one, but both. That is what I think. Why is that? Have you seen the equations people are presenting? Yeah? Say this one. They are dealing only with what? With charged oxygen at the surface. But we saw just a few minutes ago, that Falkenstein found proposes that the only species of oxygen that can dissolve are neutral oxygens, not charged oxygens. Yeah? One could think that this is a minor problem. No, it's not a minor problem. It's going to lead us to a different relationship between the variables. That's the problem. So Folkestone states then that in principle, neutrals and charged particles can dissolve, but the dissolving of neutral is energetically favorable to the point that the dissolving of ionized oxygen is negligible. So according to Folkestone, the equilibrium is established between the oxygen in the atmosphere and the absorbed oxygen, but neutral oxygen on the surface. Then, depending on where the Fermi level is, this absorbed oxygen on the surface, yeah, some of them are going to ionize, and there's going to be another equilibrium here. Yeah. Accordingly, the right equation to write, if we only have oxygen, is that oxygen in the atmosphere is in equilibrium with this. Yeah. So this is a molecule and dissociates. We are supposing that we're assuming that oxygen dissociates when adsorbed at the surface is equal to 2 oxygen, yeah, neutral. And these reactions here are almost practically negligible. So if that is the case, this is the right equation, yeah, the ratio, and then we are going to have charged oxygen. That's correct, depending on the difference, the energetic difference between the Fermi level and the absorption site. Can you make the numbers here? You have to do I did it in one step, but I think it's not very difficult, right? The oxygen, you have to write down the Fermi-Dirac distribution for charged oxygen and divide the Fermi-Dirac distribution for neutral oxygen. You make the algebra, and you're going to find this relationship. Well, this would be then the ratio between the oxygen which is charged and the oxygen which is neutral, right? Well, now we can apply the mass action law using this equation. So it's pressure of oxygen. I'm going to do, if not, I will have a lot of equations on the screen, but I think you can follow me. That is, the pressure of oxygen, which is this, is equal to the pressure of the density of neutral oxygen absorbed the surface to the square. But this is this which you have here. We put to the right, this to the left, and we can put things as a function of charged oxygen. So it's oxygen, charged oxygen to the square, because this was to the square, and we have this exponential to the square. That's right, we have the factor 2, and since that is in the denominator, we have the minus sign there. Do you follow that? Yes. No. Yes. Okay, so this is the ratio between the oxygen pressure and related to the amount of oxygen absorbed at the surface, and that depends on the difference in the Fermi level and the absorption's energy. Well, now we have to realize that EC minus EF is equal to this. Here we have subtracted and summed the absorption energy. Yeah, this difference, the difference that is related to the position of the absorption energy at the surface, which is constant. This is constant. This is number. This is constant. So, and we also know that, you remember that this amount, the amount of charge at the surface, is practically constant. So we can write the pressure of oxygen is proportional to this exponential, yeah, EC minus EF of kT. And we wanted to write down things in this way. Why? Because this E2 EC minus EF over kT is essentially the density of electrons of the conduction band, right? You remember that the density of electrons of the conduction band was AC times this exponential, right? So you put everything together, what we get? That the density of electrons at at the conduction band is proportional to 1 over the pressure of oxygen to 1/2. Amazingly, we found that the result is the same as the two previous models, when only oxygen is present. If oxygen is singly charged when it's at the surface, ionizes as a single ionized oxygen, the density of electrons at the conduction band is proportional to 1 over the pressure of oxygen to 1/2. If we do it with double charge ions, we are going to get here 1/4. So far it's the same. Problems start when you introduce a reducing gas. Because now, as we saw before, the reducing gas takes oxygen from the surface and dissolves, but the same token, by how oxygen can dissolve, the reducing gas can only take a neutral oxygen, because it takes a charged oxygen, it has to liberate an electron, and that electron has to go to the conduction band, and that takes a lot of energy. So dissolution takes place through neutral oxygens. So under steady state, as we did before, the absorption rate is going to be proportional to the pressure of oxygen, and we have two channels for desorption. Natural desorption due to oxygen at the surface, and now we have a second channel for desorption due to the presence of the reducing gas. If this is correct, that is going to be proportional to the pressure of applying the law of mass action. This is going to be proportional to the pressure of the reducing gas and the amount of neutral oxygen at the surface, right? Again, if the reducing gas is playing the dominant role, the relevant role, this term has to be much bigger than this term, so we can consider this can be neglected, and then we can deduce that the amount of neutral oxygen at the surface is proportional to the pressure of oxygen and inversely related to the pressure of the reducing gas, right? And now we have to do a similar analysis than before. I'm not going to repeat it. This you have to change the oxygen, like it's equivalent with this, the density of charged oxygen divided this exponential. We do all the same, and this exponential essentially, what we count from this exponential is proportional to the Fermi level position. And n, the density of electrons at the conduction band, is essentially proportional to the exponential of where the Fermi level is. So we do the same than before. We are up to this, and we can find that the density of electrons at the conduction band for our model 3 is proportional to the pressure of the reducing gas and inversely related to the pressure of the oxygen, the pressure of oxygen. Okay, so we have here the results, all the results from model 1, the Japanese model, the German model, and this the Russian-Argentine model, I would say. So, and here we have an outline of the surface reactions involved. Here alpha is the charging of oxygen, the ions of oxygen at the surface. So it can be 1 or 2 if that oxygen can be single or doubly charged. And depending on this condition, we have the two results for both models. And if you look at them, they are all different. That's very interesting. This is very spread in the literature. There are many papers, and they apply sometimes one model, sometimes the other model. And essentially, they found very different results. And the results, the experimental results, there's a lot of dispersion. And I think the dispersion in the results is because they are using large or medium-sized grains in such a way that the conduction involves the tunneling current. And since the Tallinn current depends on many details, and sometimes the grain can be partially depleted and completely depleted if we have a medium-sized grain, they found any kind of results. But we are going to make the experiments with very small grains, where this can be directly applied, because in that case, the conductivity is directly related to the electron density. Yeah. So we are going to make the experiments to check which one is correct, or apparently which one works. So this was our experimental setup. Everything is very simple. It was built by a student of mine who went to Germany, who worked with a guy we don't agree with. He didn't know that. So he came back and could build this system. It's not very expensive. These are the expensive things because they control the flows of the gases. And this is just to measure the resistance. And it should be here. Here, this is the chamber. It's amazingly small. This is the chamber, the thing on the left. Yeah, you put there the sample, and the gases come in. They're mixed up here, and they go there. And then there's a couple of things to measure, a couple of cables to measure the resistance. So we're going to measure first the conductivity as a function of the oxygen pressure. Always, everything has to be done with dry air. If we have humidity there, things change completely, the physics changes completely, and people do not agree what's going on either. That would be a second challenge in my life to find out what happened with humidities there. And then we are going to measure the conductivity as a function of the pressure of hydrogen. We use hydrogen as the reducing gas at the constant pressure of oxygen. Then we are going to measure the conductivity as a function of pressure of oxygen with the pressure of hydrogen constant. And then we are going to measure the conductivity keeping constant the ratio, changing the pressure of hydrogen and oxygen, but keeping the rate constant. Okay, so first result. Conductivity as a function of air pressure. And we found these are the experimental points. We like them a lot. When we did it for the first time, they're quite well aligned. Yeah, we couldn't believe it. And we got this is in log scale, so the slope is the exponent. Yeah. So we found out that the exponent is 0.24. We couldn't believe it. We were so happy when we found these results. There are a lot of approximations we have done, but it's quite close to 0.25. Yeah, and it's quite far from 0.5. That would be the exponent if oxygen adsorbs as singly charged. So this result, that the exponent is practically 1/4, is telling us that the oxygen adsorbs doubly charged. Something that now is having more and more consensus. More and more people are saying that this is species of oxygen adsorbed at the surface. So far, the three models work. And the three models work considering that the adsorbed oxygen can be doubly ionized, right? Well, we go now to changing the pressure of hydrogen, yeah, keeping constant the pressure of oxygen. And we found an exponent was equal to 0.47, very close to 1/2. So model 1 would work if oxygen would absorb singly charged, but we have shown first that it was doubly charged. So this is not compatible. So model 1 does not work. Models 2 and 3, work for doubly charged oxygen. So far, models 2 and 3 remain in the game. This one was eliminated in the place of, making reference to the World Championship, soccer. So these are the two possibilities we have so far. Well, next, we measure the conductivity as a function of the pressure of air. We got again, a dependence very close to 1/2. And so 1/2 would be fine for model 1 if oxygen were singly charged. Well, we saw that it's doubly charged. And model 2 does not work. The only one that works is model 3. That works for doubly charged oxygen. So everything is consistent for model 3. Yeah? And also if we this experiment as a function of the pressure of air, but keeping the ratio constant, that if we kept the pressure of hydrogen 0.2% of the pressure of air, and essentially nothing changes. So the exponent has to be the same. If you are changing, if the exponents for air and for hydrogen were different, this should show should show a change, but no change is seen. I mean that if this exponent is the same, I can change the ratio, the pressure of the reducing gas and the oxygen, but if the ratio is the same, this number is the same. And that wouldn't happen for model 2, since the exponents are different. And this obviously does not work because it shows 1/4 and it should be 1/2. So we believe that model 3, the model based on Falkenstein theory of adsorption, is the correct model. Okay, so then we theoretically determine the expected exponents applying the mass action law. According to experiments, the response of tin dioxide is consistent with an absorption model derived from the Falkenstein theory, what we call the model 3. And we found that oxygen ionosorbs as oxygen minus minus, 2 minus. But it adsorbs and desorbs a neutral species, as Falkenstein proposed. Okay. Amending here the subject, it was what was the dependence on the gas pressures of these sensors, and from this dependence, what we think is going on, right?
Just a couple of questions. So this is all just small grains of.
Yes.
But do you see any grain worsening because you're heating this at 300?
Yeah, if you heat up more than that, you end up with larger grains. The larger the grains, these relations deteriorate. That is, you start having here different slopes, which we attribute, I think, is because of we start having band bending, and if you start having band bending, you start having tunneling current, and that depends on the details and the dispersion of the grain, the size of the grains. But we are really very happy, because we didn't know what we were going to find, but essentially the exponents we are finding are very close to what the theory is predicting, even though we have made many approximations. But as the grain gets larger and larger, these things change. Essentially, they increase. The dependence with the reducing gas increases, and this is what you find in the literature. Most people find larger exponents.
And so you have the microstructure after you do all your measurements?
Yeah, we go to the X-rays and also using Raman spectroscopy. Yeah, and we found the size of the grains, and up to 6, 7 nanometers, this works well. And the larger the grains are, it deteriorates more and more.
And the second question is, if you are doing this with a P-type oxide, will it just be a flipping over of the analysis, or it's not so simple?
I think the analysis in principle should be the same, it would be symmetric. But We should check it. Yeah, we never did experiments. We are doing tin oxide because it's the most popular oxide used in gas sensing. We should check it with zinc oxide. I think would be a good first.
So zinc oxide would still be N type, right?
Same time.
So I can understand oxygen absorbing as O2 minus because I have excess electrons in the conduction band.
I guess it's going to be the same. I'm not sure.
But P type there will not be any excess electrons. Will absorption even happen or?
Yeah, I don't know. I should think about that. It's a good point. I should think on that. I should make the analysis.
Yeah.
You see, that analysis is very basic. That is, you're using things you know since the first courses in chemistry, but it takes some time to write down things, and you have to do it very carefully. You can confuse yourself very easily. I don't know, because in that case, what is a way people really use to check if you are dealing with an N-type or P-type semiconductor, putting oxygen and seeing if the conductivity increases or decreases.
Oh, okay.
So if it decreases is N-type, if it decreases P-type, as people do regularly. But what is the rule you're going to find? I don't know in principle. It should make the numbers. Well, next steps in my research will be to play with another semiconductors, in particular P-type semiconductors.
Because that's something we haven't looked at as well. We are normally when we do these, it's all N type, right? Never really seen much of.
Okay. Well, some topic I would like to talk about. Semiconductor heterostructures. I've received regularly many manuscripts to be a reviewer. Most of people working in heterostructures in this field, they do it wrong. Yeah? I cannot believe it. Something very basic, but they can be very confusing. So I think this is a good point to tell you that be careful with this. An heterostructure is a junction but between two different semiconductors. I think many of you must know this even better than me. Yeah. Okay, let's consider a junction between an N and a P type semiconductors. Yeah. So let's suppose that the situation is this one, for example. This is electron affinity. This is the gap. We have here a different gap. This is a p-type because the Fermi level here, yeah, is low, and this is an n-type. As you see, the Fermi level is higher, close to the conduction band. So the question is, how do this structure, when you put it together, how they are connected? How do you do it? I remember many years ago, this was a national task of the Italians. If you look in the literature, you're going to find out many papers published by Italian groups. Apparently, it was a national task that they were working on this. The first results using photoemission, I remember, were done by a guy called Giorgio Margaritondo. If you find out, Margaritondo, look at that. I don't know, I guess that guy must be retired now, I guess. Well, the first rule we can apply, which is the simplest one of what people try to apply, unfortunately this rule works quite well for ionic semiconductors. Does not work for covalent semiconductors, but if you deal with ionic semiconductors, that's by practice, I know it works quite well. But at least it's a good first approximation. Well, according to electron affinity rule, the difference in the conduction bands is just the difference between the electron affinities. Yeah, that is called the affinity rule. And here I'm telling you, advising you that not always work well, because we are using a bulk property, semiconductors, to predict something that happens in an interface. But well, it works quite well in principle. So if this is the difference, which is, we can see it in this picture, in this scheme. If this is the electron affinity and this is electron affinity at the interface, and this is the key point, you have to make the drawing at the interface and forget for a while about band bending. If you introduce band bending initially, you are going to get confused. So you have to know what happens at the interface, specifically at the interface. Forget about in principle, about the band bending. If you apply this rule, then what we are looking here is, okay, this is the vacuum level. We consider vacuum level constant, have to be the same. If this is the electron affinity 1, the other electron affinity, so the difference here, yeah, the discontinuity in the conduction band has to be the difference. And that's the electron affinity rule. Seems to be very simple. So if this is the discontinuity in the conduction band, the discontinuity in the valence band has to be look at this. This is the gap here, and this is the gap here. So the difference between the gap here is going to be the total difference, this plus this. Yeah. So the discontinuity in the valence band has to be this difference minus the already difference between the discontinuity in the conduction band. So this discontinuity is going to be the difference in gaps minus the discontinuity in the conduction bands. Well, once you have this, yeah, you have the problem solved. Now the problem is that the Fermi levels do not match. So what is going to happen here? Well, we're going to have band bendings. And where exactly the Fermi level is exactly at the interface depends on the dopants, the dopant concentration of both sides. You can make those calculations, but essentially, let's see first this. There are considered 3 types of unalignment types depending on how they match. This is considered a type 1 interface with one band gap is between the other band gap. The other one is called staggeret, this one, and this is called broken gaps. Well, once you know this, you know what's going on at the interface, and now you have to match this with what's going on at the bulk of both semiconductors. So what we just draw is this, but you already know how much is this, how much is this. You make the drawing here, yeah, very close to the interface, and then depending on the dopings on one side or on the other ones, you are going to have band bendings, yeah, because at the bulk this has to be N type, and here at the bulk this has to be P type, yeah. But if you draw this in your first step, I can guarantee you are going to be lost, yeah. It's very confusing. So first you have to know where these levels are, and then you make the band bending, yeah, in such a way that you arrive at the bulk with a p-type and a p-type semiconductor. It seems to be simple, but it's very confusing. And it seems to be very confusing for many researchers, because I regularly receive, I can tell you, manuscripts from all over the world, and they're wrong. And they don't know how to match things, and you can find any kind of things, yeah? Okay. So I feel, well, now that I have advised you about this. Be careful with this. Seems to be simple, it's not simple. Surfaces are not simple. Okay. Well, now I'm going to tell you about some practical aspects of some things we have been working in Argentina from these sensors. You're going to find out some things in Spanish. Sorry, I don't have it in English, but the Spanish is you're going to have an extra class on the Spanish. You're going to learn some Spanish. You're going to see that the technical Spanish is very close to English, the technical English, because they are using Latin words in science, and Spanish is a language derived from Latin. So we were doing this in principle. The motivation was the carbon monoxide. Many people I don't know here, I don't have statistics from here, but in Argentina there are many problems with heating. That is, ours is much colder place than this one. So during the winter we have to use heating. And the typical way of heating is burning natural gas. There are pipes of natural gas who arrive to houses, and we cook with that, used in the kitchen and for heating. And if the combustion is not good, that can produce carbon monoxide. Yeah? And many people have been having troubles with that, and many people die regularly. I don't remember exactly the numbers, but there were dying more people due to carbon monoxide intoxication than in airplanes accidents. But when you have an airplane accident, it's in all the news. Yeah, because I'm saying things that aren't very nice, but I'm going to talk them openly. Yeah, when an airplane crashes, maybe they die 100 people, 200 people at once. So it's in the news. Yeah, because of carbon monoxide intoxication, they died much more than that, but not all at the same time in different places. So it's not seen by in the news and don't appear in the news. You don't have the impact in the news that an airplane crash has. Well, how is carbon monoxide generated? Well, here on the right, here says when the amount of oxygen is enough, is sufficient. That's enough. When you burn whatever you burn, you're going to, anything having carbon, is going to produce carbon dioxide and water vapor. Don't know if you understand this. In Spanish is dióxido de carbono, carbon dioxide. You see, it's the same. Vapor de agua is water vapor. Okay, if that is the case, you're producing carbon dioxide. Carbon dioxide is not poison. That is, produces nothing unless you have a lot and it's replacing oxygen. Then you die because you don't have oxygen to breathe. But it's not a problem. If that is the case, do you cook? You use natural gas for cooking as electricity? What do you use here? Oh, it's gas. Ah, good. Good. You're going to have, maybe you have this problem. Okay. If you see at the flame, if the flame is producing carbon dioxide, the flame must be mostly blue, yeah, light blue. As soon as you don't have enough oxygen, because maybe you consume the oxygen in the environment, or maybe the mixture is not well done by the heater itself, or at the kitchen, then you can produce carbon monoxide, and then the flame becomes more yellow. Yeah. So that's a way of taking a look immediately to see what you are producing. Okay, this is safe and this is unsafe. What is the problem with carbon monoxide? The problem with carbon monoxide is odorless, it's colorless, it tasteless. I don't know how to taste carbon, but this is in many papers. I never understood what is tasteless. Well, it does not irritate your eyes or whatever. Yeah. And as it says here, it's produced from the incomplete combustion of natural gas and other products containing carbon. When interestingly, carbon monoxide produces more than 50% of poisoning as the most common cause of death from poison. It is all over the world. One of the causes of its origin is the poor condition of the facilities. Maybe you have a leak or whatever. There is not enough ventilation. The installation is not correct. Yeah. So we focus on that as a practical application. We have been studying at the lab, yeah? And we develop a device to prevent this type of accidents. Yeah? Well, the first thing you have to do, as I said here, is to keep your appliances in good form, in good shape. Yeah? typical things that are in the market, at least in Argentina, are alarms. That is, we have sensors of carbon monoxide, and the carbon monoxide reaches some point, an alarm starts, whatever. Some sound, for example, to tell you that something is wrong. But the problem is you are sleeping and you don't hear the alarm, you're in troubles. Also, if you're not at home and you left there your pet, bad luck for your pet. So what we were looking for was not only for something sensing, but something that sense the gas and do something, yeah, to prevent the formation of carbon monoxide. So I'm going to tell you what we developed or what we did. This is very engineering. Well, what should we do to avoid carbon monoxide accidents? Well, in principle, that's the things that you find in the website of the company of distributing gas, yeah, in our country. And they tell you about the installation that has to be in good conditions, and periodically you should check the appliances. Here we have a drawing with this, but it's funny, but it's terrible, yeah. You have the guy here which is astonished because of the gas outlet, some birds built there something, yeah, their nest. This prevents the gas going up, so it cannot go out, so it's going to go in. Yeah, someplace have to, the exhausting gas have to go someplace. So this is very dangerous. You have to check for this. These things are very usual. We have a lot of pigeons in our country, and they make nests at any place. Well, we have to use heating for heating, but we don't have to use kitchens for heating. They are not prepared for that. So we are here's a guy heating his hands using the oven. The oven is consuming, typically in a kitchen in a house, is taking the oxygen from the ambient. Yeah, instead of that usual heating, you have a heating device, it's taking oxygen from outside. It's burning, gives the heat inside, and the exhausting gas go outside too. And my city in particular is first ranked with accidents with carbon monoxide. And the reason is because my city is Mar del Plata, I tell you. It's the biggest touristical city in the country. So there are many people having small apartments that are empty during the winter. And they go to the city during the summer. So appliances were not taken care. The apartment was without any care of anyone. So it was very cold. The winter in my city is very wet. So many times they arrive to the city and they don't care if they turn on things, and maybe they are not working well. Yeah. So that is the reason, yeah. And here's an example of someone who took a picture of a guy who was cold, so he put his bed close to an oven and turned on the oven. Yeah, this is quite suicide. Yeah, but these things happen. Okay. Yes. Sorry for the Spanish, but it's very easy. These are the effects of carbon monoxide. These are the percentage in part per million. Yeah, and this, tell me it's easy for you. Hours of exposition. Isn't it easy? You see, you're learning Spanish. Hours of exposition. This is perilous danger. Yeah? This is headache. Perceptible effects, no effect. So up to, say, 200, yeah. This is in percentage 0.02%. It's very low amount of carbon monoxide. Not much is going on, but you can have just a headache. But you see, as you go up, you don't need a total amount of carbon monoxide with 0.08%, 800 parts per million. Yeah, 2 hours of exposition, you very probably you could die. So, next point. What are the appliances more dangerous? Well, the bad guy in the movie are the bath heaters. 80% of the accidents happen with bath heaters. And the reason is very simple. We have general heaters and then kitchens. But why bath heaters are the villains of the movie? Because bath heaters are in baths, and you have realized that bathrooms are very small compared to other rooms in the house. So you don't have much air, much oxygen there. So a bath heater can quickly consume the oxygen in the environment. So most of people who died due to carbon monoxide died in their bathrooms, taking a bath. Yeah. Well, possible solution. As we say, indoor air pollution from carbon monoxide mainly came from daily activities, like cooking and heating. In any combustion process, no carbon monoxide is generated, but if the installation is not good, or it's not properly installed, we can have problems. So we are looking for a technological solution to avoid this kind of poisoning. As I told you, an alarm indicating the presence of carbon monoxide is a good step. Yeah, it's a good step. Because if you don't realize of the presence of carbon monoxide, if you don't realize, you are more and more sleepy, that's all you feel. And eventually you got to sleep, and then it's one way, yeah? So anyway, it's not bad. An alarm is not bad. But we do not want a passive indicator. What we want is something that avoids the continued formation of carbon monoxide. That's what we want. We want an actuator, what is called an actuator. So these are the typical devices we use. I don't know if you use this here. A heater has a thermocouple. Yeah? So as I mentioned, what a thermocouple is, it's just a junction between two kinds of metals. When this is hot, that produces a potential, different potential, and this different potential can create a current, and that current goes to a solenoid, and that is what's keeping a valve open. So when for some reason there is no much more gas, or for some reason the burning stops, automatically the thermocouple stops sending that voltage to the solenoid, and the valve closes, and there is no more gas running through the heater. But in that case, it's not big. The problem is not the carbon monoxide, but the gas, which is going to be all over the place. Well, but this is the system that is usually used. I mention this because we have now to solve an engineering problem. It's not a problem of physics. We have to think in a device that prevents the formation of carbon monoxide. It has to be simple, has to be effective, but it also has to be cheap. Because it's very expensive, you can make a very expensive and fancy thing, but if the heater doubles its price when it has that device, no one is going to buy it. Yeah. So we have to do something reasonable, cheap, and that works simply and well. Okay. So this is a picture of what is called a magnetic group. It has essentially a spring that keeps the valve open. So keeps the valve closed. To open the valve, I don't know here in Argentina, you have to push it for the gas to pass, and then you turn on the gas with the spark, with the same device. The device itself has a spark, something to make a spark, and then you have to keep it for a while, and all we have to wait is for the thermocouple to heat up, so the current establishing, and this solenoid, which is here, is going to keep the valve open. If for some reason the burning stops, you don't have more the current due to the thermocouple, so the valve is released and closes the entrance of the gas. Does it work that way here? It's more or less the same system you have? No. More or less? No. Okay. So this is a basic safety device. Yeah. Usually it's in Spanish. Basic system of protection for lack of flame. It's quite close. Yeah. Okay. You have the thermocouple here, and this and a small fire there. Yeah. We call it pilot flame. That is heating at the thermocouple. The thermocouple goes, and we go to that magnetic system, magnetic group, which keeps the line of gas open. As soon as this does not work, there is no burning of the gas. This current is not running any longer, and when that happens, the line of gas is closed. Yeah. Well, this is what every regular device has. Typical heaters that are sold all over the country, or my country, I would say. Well, we have to do something very simple. What is the most expensive part here? Is the valve. Anything being mechanical is not cheap. Yeah? So what we did was the following, and it can be done in already built or constructed heaters. We open the line of the thermocouple and put there a relay, this relay, an interrupter relay, which is controlled by some electronic. It is quite simple, which responds to the detector of carbon monoxide. So in that way, we don't have to introduce another valve because this is expensive. So all we have to do is to put here a relay which is controlled by the gas detector. And all this was about only $7. We could build some prototypes with only cost $7. I don't know. That was about 3-5% of the total cost of the heater. So that's unreasonable. Okay, so I ended up with this. That's why I say thank you for your attention. Okay, we are going to start then with the exam. We're going to do it all together. This is the type of exams I usually take in Argentina. Maybe this is a little longer, so we have more subjects to discuss. To warm up, I usually start with some true-false statements. So the students have only to say if this is true or is false. Yeah. So this says, first one says, the group speed at the edge of a brilliant zone reaches its maximum value. It is right or wrong? Wrong, right? If we have at the brilliant zone, like this would be K. This is P over A. This is E. I'm not used to use these things, sorry, I do my best. So at the edge of a brilliant zone, yeah, the dispersion relation reaches a maximum, and here the derivative is 0. And the speed is related, you remember? This group of speed was 1 h bar derivative of E respect of K. And there the derivative of E respect of K is 0. So far so good. Next question. The energy of a gas of electrons in a solid can be calculated to a first approximation, considering that each electron has an energy equal to 3/2 of kBt. Sorry, this B should have been a small subscript. That's the constant Boltzmann times the temperature. So in a regular gas, in a gas made of nitrogen, for example, and oxygen, the atmosphere, this would be correct. You know, this is a partition theorem. In any direction, we have an average energy of 1/2 of kT. Since we have 3 dimensions, we have 3/2 of kBt. You remember that? Okay, that would be correct if we were dealing with a classical gas. A gas made of particles that behaving classically. But is this correct for a gas of electrons? No. We can make some democratic, we can vote and decide if it's correct or not. Well, why this is not correct? Because in the gas of electrons we have the distribution, the density state as a function of E, and this was at 0 Kelvin. And the gas of electrons, if you increase the energy, it does something like this. Remember that? So the energy that this is the Fermi level. This is the reason why a gas of electrons has a very low heat capacitance. Did I explain this? No, I think I didn't explain this. In a regular gas, the energy, the average energy of a particle is 3/2 of kBt. So as the temperature increases, the average energy of every particle increases proportional to T. And it changes like this. So the people at the beginning did not understand why in a solid the electrons practically did not contribute to the heat capacitance. They should contribute almost as much as the lattice itself, but it does not contribute almost to heat capacitance. And the reason is here. You change the temperature, and I'm exaggerating making this. Yes, the change in the distribution practically does not change with temperature. The only electrons that change a little their energy are those which are close to the Fermi level. Most of the electrons cannot do anything. So here every electron is changing their energy. Here only those close to the Fermi level changes. And this is the reason why the gas of electrons practically does not contribute to the heat capacitance in the solid. Okay? So this statement is wrong. Each electron does not contribute to this amount of energy. This is true for a classical gas. Okay? Number 3. The free electron theory gives rise to a dispersion relation of the type E2 proportional to k squared, and the effective mass is the same for any value of k. Is this correct or not? No. No. How do you say? Do you confuse me many times? When you say yes, it's like something like this. For us, yes, it's like this, and no, it's like this. So, am I right? You move the head a different way? No, you didn't answer. You laugh at it. You didn't answer. Well, the electron theory, the free electron theory, says, gives a relationship of this type. E as a function of k. It's correct. It's proportional to k squared. And you remember that the effective mass was h squared over the derivative, the second derivative of E respect of k twice. Yeah? So we have to derive this twice. Yeah? But this is a parabola. So the second derivative of parabola is a constant, right? So the effective mass is the same from the value of k. This is correct. But you have to be grading yourself, saying how many you are successful and how many answers you are not successful. Let's see this. Here it says the chronic penny model tells us that certain materials can be metallic as a result of overlapping bands. True or false? I heard something. Well, we found that the chronic penny model was the first model. It was a paper written by a guy called Crony and another guy called Penny, who wrote the paper in 1927. And they introduced the first model that explained the appearance of bands in a crystal. And the model is a one-dimensional model. Yeah? In a dimensional model, overlapping does not happen. Yeah, does not take place. Band overlapping is more than one dimension. It's a two-dimensional, three-dimensional phenomenon. So this is false. This is not correct. You remember that in the chronic penny model, we have bands like this, separated by other bands like this. It was K and it was C, yeah? And there appear band gaps here. These are allowed bands and these are forbidden gaps, yeah? And overlapping takes place because in more than one dimension you have some band like this, but maybe in either direction. This is 100 and 111. You have another band, and that other band can make something different. Then this band overlaps with this one, we're going down, and then the band gap disappears. Yeah, this is more than one dimensional problem. Okay. If you have any questions, interrupt me anytime you want. In a one-dimensional crystal, the effective mass is always positive. This is correct or false? False. Good. Yeah. In the chronic penny model, we saw just the chronic penny model, which is a one-dimensional. The first band does something like this. Here at the bottom, the second derivative, remember that the effective mass depends inversely on the second derivative of the energy, yeah, respect of k. In the bottom here of the band, the effective mass is positive, but at the top, the second derivative here is negative. And so the effective mass has to be negative. Yeah? This is not a two-dimensional, three-dimensional, yeah, phenomena, but this universal phenomena. Okay. How are we doing? Tell me when you're tired. We are tired since a couple of hours ago. You're going to answer me. Okay. Well, this is a statement which I found in many books. And many books say that in metals you have band overlapping. And that is not correct. you don't need to have band overlapping to have a metal. Yeah? All you need that the Fermi level drops in an energetic region where there are states. Yeah? So the question says, all metals are conductors because they exhibit the phenomenon of overlapping bands. So this is written in many books. I have seen that they show, for example, the band like this and the other band. This is the conduction band and this is the valence band. And now they say this is an insulator on a semiconductor because you don't have overlapping of bands. Instead of that, if you have a band, the conduction band like this, and the other band, I'm going to do this just to see it, and the valence band is like this, so you have overlapping, here are bands. Now this is going to be a metal. They don't even care about making a drawing, showing what the Fermi level is. Because in this case, you can say that this is an insulator. If they ask you that, you say, I don't know. Why you don't know? Because I don't know where the Fermi level is. Yeah? If Fermi level is here, this is a metal. If the Fermi level is here, this is an insulator or a semiconductor. If the Fermi level is here, we have a metal again. Well, if we have a complete continuous case of where states are available for any energy, well, it doesn't matter where the Fermi level drops. It's always going to be a metal. Yeah, that's correct. But in the case of this, with this general case, I don't know, looking at the density of states, if this is going to be a metal or not, if I do not know where the Fermi level is. Right? We're taking the test, the exam. Yeah, but they're not helping much. I'm doing the test by myself. Okay. Where are we? 6? Okay. We take the break now? Okay. Well, okay. We continue with the exam. Now you're all rested. Okay. Next. True false statement. It's very nice. When doping an intrinsic semiconductor at room temperature with Na acceptors atoms and Nd donor atoms, the extrinsic concentration will be approximately Pi plus Na, and N is going to be Ni plus Nd, which satisfies the condition that the positive charge, which is P plus Nd, is the negative charge, which is N plus Na. Sounds convincing. Yeah, you add donors and acceptors, and then the total amount of positive charge increases and the negative charge increases, but keeping electron neutrality. That's the trick. Yeah, I'm expecting you, oh, we are keeping electron neutrality, this must be fine, that must be correct. Well, in fact, this is incorrect. Yeah, you cannot increase both simultaneously, the N-type, the N density and the P density. Yeah, the number of electrons and holes. Yeah, you cannot increase both of them at the same time. You have only one Fermi level. So if this is EC and this is EV, eventually we end up with a Fermi level. If the Fermi level is up, you're going to have more electrons and just few holes. Is the other way, you're going to have more holes and less number of electrons. But you cannot increase both at the same time. If you try to put dopants, donors and acceptors simultaneously, they cancel each other. That's one of the reasons it's very difficult to make, for example, tin oxide, make it as a p-type semiconductor. And this is something I did not mention. Usually then, tin oxide, I know that very well for tin oxide because it's the oxide I have worked the most. But usually things are like this. The Fermi level is an N-type, is close to the conduction band. This is conduction band and the valence band. Well, you say, well, I want this to be of p-type. What do I have to do? Well, we have to add some acceptors, impurities here, and then the Fermi level is going to drop. Yeah. In principle, this should work, but it doesn't work. Why it doesn't work? It doesn't work because as the Fermi level goes down, the formation energy for oxygen vacancies decreases. Yeah. So it's very difficult to do it. Why? And it's going to compensate the the doping due to the acceptor levels. And the reason for that is once you create it here, the Fermi level is low. Yeah, when we created a state here, the electron which was here, yeah, respect to the Fermi level is in an upper, yeah, energetically is above. So as the Fermi, sorry, this would be here the donor. It's from the donor to here. So it's like making a stone, say, in the floor level and having the same stone, yeah, in the fifth level, yeah, and being in a building. If you have a stone in the fifth level, you can throw it back and you have a lot of energy, right? Because you are creating the stone with height, so you have a potential energy. So if the Fermi level is lower, the energy of the electrons you are creating there is higher. So you are gaining this extra energy when creating a donor level. So, and that counts in the formation of the oxygen vacancy. So as you're pushing the Fermi level down, including acceptor levels, the Fermi level goes down, and automatically it's easier to form oxygen vacancies, which are going to compensate what you have done. So that is the reason why it's very difficult to make p-type tin oxide, for example. And this happens in any semiconductor, essentially. Yeah.
So
No.
what about non-oxide semiconductors, for example, gallium
No, in those kind of semiconductors, we don't have the problem because we are essentially the gap is much smaller, so the Fermi level does not move much, and everything is quite stable. So in that kind of semiconductors, you introduce some impurity, and everything is quite stable. So that problem does not arise there. But in this kind of semiconductors, in ionic semiconductors, in oxides, already at the regular situation, the formation of an oxygen vacancy is low enough for the vacancy to form. So you already are in a situation where the vacancy is formed. So as long as that energy is reduced, you're going to have more defects. But in case of gallium arsenide, you don't have it's not energetically favorable. Yeah? And also the Fermi level cannot change much. Yeah? This is about 3.6 eV, and silicon and gallium arsenide, the width of the gap is less than half of this. Okay. Eight. True, false. It says an isolated metal plate with different work functions on each side must have a non-zero charge density on at least one side. Wow, what is this? Let's suppose we have a piece of metal, and it says that the work function here, how do we call it? Phi. Here phi 1 and this is phi 2. See? And say that phi 1 is not equal to phi 2. This work function on this side is not the same as this side. Yeah. Now this is saying that the statement is saying if this is the case, we must have a non-zero charge density on at least one side of the plate. Why is that? Is that correct or not, to start with? No, I told you that the work function was it's not an easy concept. Well, the answer is this is correct. This is correct. If this were not correct, let's suppose we have electrons here. Yeah. So let's say that phi 1 is smaller than phi 2. That it's easier to take out an electron here, yeah, on the upper, yeah, the upper side of the plate. So I could make this and come out here. If I do that, that costs me no energy and end up here, and now I drop into the plate. But since phi 2 is larger than phi 1, I get more energy than I needed to extract the electron. This is a perfect continuous machine. Yeah, how do you call it? Continuous machine? Perpetual machine. Yeah, I'm gaining energy from nothing. So something must be wrong here. And what is wrong? What is wrong is that from going from here to here, I must spend some energy. I need some energy, and that energy is coming from recharge distributions. Yeah. So, and the work I need from going from here very close to this surface, or going to this side very close to the surface, has to be exactly the difference between the work functions. And how that is done? Well, this surface has to be negative charge and this positive charge, or depending if the whole thing is charged or not, there has to be a difference in the charge in one side with respect to the other one, in such a way that going from one side to another one, yeah, it costs me energy, right? So, depending on the work function of the surface, in a metal, the surface of the metal can be charged in a different way. It's very subtle. Non-professor always taught me that. I learned that by, we say, it cost me a lot to learn this by myself. I was lost for a while with this. It looks simple. Once you understand, it's as usual. Once you understand something, it looks simple. Yeah. But before that, you can be confused.
Yeah. To sort of add on to it, so let us say I have something, a gas that is absorbed on one side of a metal, that can change the work function, right?
Yeah, definitely.
So that would basically cause then, this is nothing but a potential that's developed within the metal.
Yeah, if you change the work function, you are going to have the surface charged in a different way. Yeah. Another surface. Yeah. There is no way out. If that is not happening, you arrive to things which makes no sense, like having a perpetual machine, yeah, things like that. Okay, another question. How are you doing so far? Well, at odds with a semiconductor in a metal, the conductivity varies, and thus the mobility of its electrons. Is this correct or not? It is the same in a metal and in a semiconductor, or it is different? I think I mentioned this while talking. This is correct. That is, in a metal, the density of carriers is practically always the same. Yeah. So what controls the conductivity in a metal is the mobility of the carriers, that is, the electrons involved. I remember when they are not used any longer, but when I was your age, more lamps were incandescent lamps. Well, small lamps were in vacuum. Have you seen that? And they have a small filament there of a metal, usually was tungsten, and was heat up to the point it started irradiating light, and that was the way we got light. Now the sources for light are very different, but that was that way when I was your age, not many years ago. So it was something very interesting. That is, in the time you turn the light on, the current was about 10 times the current in a steady state. Why? Because the filament was cold. And once the filament becomes hot, since now the mobility of electrons was much lower, yeah, the current was 10 times smaller. Yeah? I can tell you an anecdotal event, since it's the last day I'm allowed. Yeah, I remember arriving to the place my mother used to live, and I saw the lights on in the house. And hey, mother, you say, or mama, I don't know. Why do you have all the lights on? Oh, because the technician came to solve some electrical problem, and he told me that the time I turn on the light is when the consumption of the bulb is the highest. So I'm not turning it off, because when I turn it on again, it's going to consume a lot. Did you understand? And I said, mother, I know what that technician wanted to say. I understand that happens, but that was just less than a second. It's nothing. It's not going to contribute to the total consumption. Don't worry. Turn off the lights. You are going to receive a very huge, bill for this. She told me. You know, we are always kids for mothers. Yeah. She told me, don't tell me you know more than the technician. And I said, well, I don't know much more than other people in many aspects, but in this specific topic, yeah, I'm supposed to know. I'm an engineer, I'm an electrical engineer, I know these things. Well, eventually, she was not very convinced, because she was my mother. So she raised me up, but that kid can know. So eventually she turned off the lights, but she was not very convinced. Okay. Well, fluctuations of barrier heights at intergranular surfaces do not present a Gaussian distribution. It's true, very well. This is what we talk about. Yeah, intergranular barrier heights, vary at the surface. Yeah, essentially they are not constant, but the distribution of the barrier heights do not follow the Gaussian distribution. Yeah? It's close, but the problem is it departs from a Gaussian distribution on the sides. And that in principle could not be important for other problems, but for us in this specific problem, this is very important. Yeah? This is very important. Okay. But more complicated things, multiple choice. Yeah. Here it says that in a metal, the fact that the ambient temperature rises 10 degrees, what does it do? Does not alter the Fermi level distribution. This is not a function of temperature, because it's a very important change in the Fermi Dirac distribution. It strongly alters the Fermi level. It slightly alters the Fermi level. We have a metal. We change the temperature 10 degrees. What does it happen? Is the Fermi level going to change? The Fermi distribution essentially is not a function of temperature. Yeah? It's not going to change. The Fermi level is going to change a little. It's going to change a little because I show you how the thermocouple works. Yeah, and you have in the metal essentially goes like this. At 0 degrees, this is the situation. Yeah, all these states are filled. This is Fermi level. This is the energy, and this would be G of E, the density of states. So in a metal, this grows parabolic. This is proportional to the 1/2, and 0 degrees does happen. As we increase the temperature, it goes like this. And the Fermi level is the level at which, G of E is the Fermi level is 1/2. Yeah, the probability of occupancy is 1/2. So when you change the temperature, yeah, this point would be the same if this area would be the same as this area, because the number of electrons should not change. Yeah, it has to be the same. But the problem we have here, from here to the left, the density is lower than here on the right, because this is growing like e to the 1/2. So it cannot be exactly the same, because if it's exactly the same, the number of electrons would change. So this point have to move a little to the left to compensate for that. Not much, yeah. But this is essentially the principal work of a thermocouple. You put two metals, and with this change, because this is not exactly the same in one metal and the other one, when you change the temperature, the Fermi level changes, but in a different manner. In such a way, when you have a contact of two metals, yeah, the Fermi level, yeah, changes different one with respect to the other, and so in the other ends we have a voltage difference. Yeah, that's the principle of working of a thermocouple. Right? Interrupt me anytime you have a question, please. Maybe I'm not going to understand you, but Raman will translate to me. Yeah? Oh, this is a very conceptual question too. Consider two identical metallic cables. They have two cables, 1 meter and a Fermi level, yes. If the wires are brought into contact, we'll end up with a single cable, but twice as long. The question is, when you do that, the Fermi level of the set is lower, Fermi level of the set is higher, the Fermi level does not change, or the above are incorrect. The Fermi level of the whole cannot be compared with that of the parts. That is, if you have a piece of metal which is bigger, you're going to have more electrons. Yeah? So you could think, oh, I have more electrons, I have to accommodate the electrons. Electrons are fermions, so, oh, the Fermi level is going to go up. Right? What is wrong in what I'm saying? Something must be wrong. What is wrong in what I'm saying? As you have more atoms, the density of states also increases, proportional. Do you remember the number of available states grew up with the number of wells? You remember that? So as we have a large piece of a metal, you have more electrons. At the same time, simultaneously, you have, in the same way, you have more, the density of states grows proportional too. So in a macroscopic piece of metal, you have a macroscopic piece of 1 kilo and 2 meters or 3 meters or whatever, you have a kilogram of copper of 2 kilograms, is the same. The Fermi level is going to be at the same place. It's not going to change. Right? Seems to be simple. If you have the ideas clear, they're simple, but they can confuse you. You have things very clear.
So, Celso, if I want to confuse the students,
that's the idea.
I will just say, instead of 1 meter, I have two metal pieces 1 nanometer in length, and I bring them together. Will the Fermi level change?
Well, if the things are very okay, they can answer. We're taking very small pieces of.
Yeah. So now it's no longer 1 meter, right? 1 meter is still bulk. What happens if I have 1 nanometer of a metal? What do you think is going to be the answer? Will it change? Will it be higher, lower? Does it change? I don't know about the last one, but maybe the last option also.
Yeah, the last option is just to confuse the students. No answer. I'll explain. You raise it.
I raised it. I have explained it.
Yeah, you raised the question.
So See, that's the bad part, right? I only know the question. I don't
I don't know.
But I will try. So
Yeah.
I would argue it differently, right? So
Okay.
I think as long as I stay next to you, the mic will pick up. So the question is, what is the Fermi level now? If I have 1 nanometer, what exactly is the Fermi level? So the way I would argue is, let's say I have a box that's 1 nanometer in length. Typically, if I have a metal, we say 0.3 nanometers is the spacing. So A is say 0.3 nanometers. So I'm going to assume that my box has 3 atoms, right? So I have 3 atoms in my box. Each atom is going to give me 1 electron. So it's assuming that there is a valency of 1. So I have 3 electrons. So now I'm going to say how I'm going to fill 3 electrons in a box. And this is what we did in quantum mechanics. So it's particle in a box. You have the lowest energy state, let's call it E naught. It's not 0. Then you have E1, E2, and so on, right? And the energy E is just n square h square by 8 ml square. So if I have 3 electrons, I would put 2 electrons in the lowest most energy, and we do that because they are fermions, so I cannot have more than 2 electrons. Then the third electron would go here. This is the highest occupied energy state, so I will call this the Fermi level, right? So that's my definition. So now I have a box that's 2 nanometers wide, because I have now joined 2 1 nanometer boxes, but this has now 6 electrons, right? 3 from each box. So again I have E1, E2, E3. So if I put 2 electrons here, so this is now my Fermi level. So this corresponds to n equal to 3. So the energy E is 3 square h square by 8 m 2 square is 4. This energy, the Fermi level, is I'll write it here, is n is 2, so 2 square h square by 8 ma square. So this is essentially a constant. So this is 4, this is 9 by 4, so 2 point something. So overall the Fermi energy would drop. But that's only it's a thought experiment, right? So theoretical experiment. But that's why, since you said 1 meter, I was just curious to show you what happens if it is 1 nanometer. Yeah.
Just to play the devil's advocate,
Yeah, don't.
I'll try a question. What if, like, can we assume that there can be tunneling between at the junction?
So now there's no junction. We just have 2. So now I merge them. So I have a bigger box. So I have 1, 1. I merge them so there's a bigger box. And then I'm filling with 6. There is one assumption here. The assumption, of course, is the electrons don't interact with each other. So that we can still use particle in a box model, but that is an assumption that we are making.
Good, thank you. The general idea, this is very small. We have problems because of the discreteness of the levels. As we have more and more atoms, we end up with a solid, and we have the bands. Here we don't have bands. We have just the discrete levels. And this is also the reason why the solid forms, because as the more electrons you have, the total energy drops. Yeah? This is energetically favorable. This is what explains the metallic solid, the formation of metallic solid. Okay. Okay, in a completely filled band at 0 Kelvin, what is true? The Fermi level, the function is Fermi Dirac function is 1. V of k is equal to minus V of minus k. The total current is 0. All of the above are correct.
D.
Yeah. Therefore, B. The completely filled band. E of K. Say this is the band, and it's completely filled. All the states are filled. This is true because I told you that always we are going to have the same number of electrons going to the right and to the left because it is symmetric and all the states are filled. If all the states are filled, what's the probability of occupancy? 1. So this is fine too. And the total current, if there we have as many electrons going to the right as going to the left, is correct too. And I like this type of questions for the students because they always think that this is a trap answer. It's not the correct answer. But in this case, this one was the correct one. Right? Okay. Let's see. You are an engineer in a very important plant of semiconductors. Yeah? Just to make it more exciting. It is desired that the semiconductor have the greater number of electrons and holes simultaneously. We have a similar question before, but it's more specific. What option do you take? So, simultaneously add donors and acceptor impurities. You increase the Fermi level. You decrease the Fermi level, or you use a semiconductor with a lower band gap.
D.
Option D. Yeah, you're learning, you see? You're learning. This is the correct one. We have seen that adding simultaneously donor and acceptors, you cannot change simultaneously both the density of electrons and donors. Yeah? So if you increase the Fermi level, whatever is the way you do it, you are going to have more electrons, but you're going to have a lower amount of density of holes, and the inverse happens with C. You increase the density of holes and decrease the number of electrons. But if you use a semiconductor of a lower band gap, you're going to have more of both. Yeah? If this is the semiconductor, you have the Fermi-Dirac function, so you're going to have a little amount of electrons here and holes here, but if this is smaller, and you have the same Fermi level, you're going to have a lot of, yeah? You understand the schematic, I'm very schematic. I think you can understand it.
So, Celso, just to add to this, let us say I tell you you cannot change the semiconductor. You cannot change your semiconductor. So how do I increase electrons and holes simultaneously? So light is one. You cannot, no, doping will not increase both, right? Temperature. So you either heat it or you shine light.
Yeah. Heating up would be a solution, and from an engineering point of view, it was not very good. You need a heater, yeah. Yeah, that would be. I was thinking in a steady state, that is an equilibrium, that is another lighting.
Even in light, you can have steady state. Yeah. Once you turn off the light, it goes back.
Yeah, it comes back. Well, I should start with problems, but I have many problems and they're very, very complex. So I think, let me see, some easy problem maybe. Which one could be? Well, let's see the second one. And we end up with this. So we have with bands and things like that. Let's suppose that the energy of a band as a function of k is given by this function. Yeah? So that function has a shape. This would be something like this. Yeah? Typical we have. And this continues all the way if you want an extended. Yeah? You agree? This is like this. I'm not good drawing. Does it work? Doesn't it work? No. Ah, I have to. Okay. That's slightly better. Okay. Wow. My goodness. So, if in a situation, we want to know what is the width of the band. Yeah, the width of the band in energy goes from here to here, right? Yeah. So how much is that?
If
You forgot about this. This is just changing. It's an offset. This is a sine or cosine form. A is the height, so this is A, and this is A2, so it's 2A, right? Determine the speed of the electrons in the band. Well, the speed, you have to do the derivative. So it's 1 h bar derivative of A respect of K, and it's going to give you h bar and the derivative. This is just A sin. I'm writing everything. I'm not going to learn how to write here. Sine. Well, even worse than before. Okay. Yeah, that's going to be the speed. And we write it down. We make a drawing, I mean. Yeah. We can do it just without looking at that. You see, here the speed is 0 because this is flat. And at the top is 0 because it's flat. And the middle has to be the highest because the slope here is the highest, so it has to be something like this. Yeah. So the speed as a function of k. Quite often my drawings, but you understand what I want to do. Okay, what else we were? The effective mass. Well, to calculate the effective mass, we have to do the second derivative of it twice. So we have to derive this. Not to make a mistake, I'm going to copy from here. That is very easy. This was the derivative, so I have to derive the sine, which is a cosine. I have an extra a, so this cosine of Ka. Right? So the effective mass is going to be h bar divided by the derivative, which is a squared cosine Ka. And we have two alternatives, yeah, if we are at the bottom of the band or at the top of the band. At the bottom of the band, cosine of Ka, how much it is? It's cosine of 0, which is 1. So this is h squared over a squared. And at the top, the cosine of Ka is the cosine corresponding to the top, which is p over a, right? If we instead of k put p over a, we have the cosine of pi. The cosine of pi is minus 1. So this is minus h bar over a squared. Okay. Yeah, this is a simple way of seeing how the effective mass can be positive or negative in a band and a simple band. That is the spirit of this problem. Well, I have many other problems and many complicated. Fortunately, we don't have time. So, yeah.
any questions from you guys? If not necessarily on the sensors, even basic questions on semiconductors. Just in the spirit of what sensors being doing now. So that's been the idea, that we not only just tell you about practical applications, but also tell you some of the foundational theory, so you could think about it. And depending on what you are doing, the theory will always be different. That's also the idea.
Yes. Well, I would like to thank you for being so patient. I haven't been speaking English for years, so it's not easy for me, but I think I was improving during the week. So thanks a lot for being so good students, so patient, so nice, and it's a really great pleasure to be here. Yeah. And I see that science somehow connects people all over the world. We talk the same language, yeah, which is science. Okay, thanks a lot.
Yeah.